Good afternoon, guys. This video is being recorded as you guys are working on quiz number 1 on chapter 1, of course. I just wanna, well, it doesn't matter since you guys have different numbers, but the idea with today's video is to show you how to, or the strategy for some of the problems on chapter 4, which is motion in 2 dimensions. So pretty much like you probably have been following the video lectures, the idea now is to use vectors in 2 dimensions and just write the equations of motion. For example, in problem 1 and 2, right, you have to do that. Problem 2, sorry, in there, you have to use calculus, okay? But in problem 1, you can just use the, well, this equation here, that the position R is equal to the initial position, which is 0 because it's in the origin, plus the initial speed. Here I have 9I, it's going to be different in your case, times time, plus 1/2 of the acceleration, which is 2J times time squared. And that's clear. You will get 9Ti plus 1T squared J, right? So 9Ti plus 1 or just J or T squared, sorry. Let's put here T squared J meters, right? That's pretty simple. The final velocity, you will just use the equation. The final velocity is equal to the initial velocity plus acceleration time. They are all vectors times scalar, but you don't need the time. It's just in terms of the variable t. And you should be all good. To find the coordinates, you will evaluate this for t equals to 10. That's how you find the x coordinate and the y coordinate. And to find the total speed, you evaluate for time, and then you find the magnitude of the vector. So that's actually not that bad. For question 2, just remember this. I'm going to show you guys on the board. Remember that the position R of a given vector, sorry, the velocity of a particle is equal to the first derivative of the position. Now we use the R because we are in 2 dimensions. Even on 3 dimensions, you can use R. So you use that, and then if they give you a value of R, to find the velocity, you will need to do an integration or a derivative. So what do they give you here? They give you the, oh, that's easy. So they give you the value of R. So you don't even have to use this. Well, yeah, you have to use that. If they give you a random position, which I'm going to write 8I minus 4T squared, right? So if R is 8.0I minus 4.0T squared, I will do the derivative, right? So the velocity, this is constant, so there is nothing here, minus 8.0, yeah, T squared, T. So that's the velocity as a function of time. And if they ask you to evaluate, that's the answer as a function of time. Meters per second, right? The acceleration will be the derivative of this, because the acceleration is the derivative of the velocity respect of time. I have the velocity, so the derivative of that will be minus 8 meters per second squared. And then when they ask you to evaluate, that's not that bad, right? There's a problem here. Let's go into circular motion, where they give you sort of a helicopter seat that is rotating respect to this axis here, right? They give you the length of the seat, the angle between the seats, and they give you the speed of rotation in meters per second. So they give you the linear speed, the tangential speed. So the imagine this like a helicopter, right? Rotating around its axis. So like a vortex. They want you to find the centripetal acceleration. For this problem, you need to remember that the centripetal acceleration is equal to the velocity square, the tangential velocity square divided by the radius. You do have the velocity. You are going to be given that. That goes in here. So the problem is to find the radius. And look, to find the radius, you need to draw this, which goes directly from the middle. We're going to assume in this problem that there is symmetry. So it's like you have a circumference here going like this, and then like that, right? This will be the radius, 90 degrees. They give you the length. And when you have this angle is the same as this angle. They give you here, my question says 70 degrees. It might be different in yours. You just divide the angle given by 2 because it's a isosceles triangle. And then to find the radius, this is the radius here. That will be the value of L, the length of the seat, times the sine of 35. So that's easy, right? I use this. I plug this value here. And I compute my centripetal acceleration. So that's nothing complicated. The problem with a satellite, okay. So if you have an astronaut orbiting the Earth, or if you have a shuttle orbiting the Earth, normally that shuttle is going at some speed related with a gravitational pull between the planet and that shuttle. So as we leave the planet, the value of gravity decreases. And it decreases because the farther we are from the center of a body, in this case a planet, the weaker the gravity. We want to learn that more in Newton's law of gravity or gravitational law. But for now, just remember, if you have the planet, the Earth, and you have an object orbiting, you need to know the radius of the planet and then the height. The height is this, the altitude of the satellite, which in the problem I have here, I have, well, 700 kilometers. You may have something different. And they give you the radius of the Earth. So the radius of the Earth is 6,400 kilometers. And this is 700 kilometers. So you are orbiting with some speed. They want you to find that speed if they tell you that at this point, so at this particular point, the value of gravity is 8.14 meters per second squared. So that will be different in your problem because you have different values. But this is simple because we know that this is the free fall acceleration. So it's a radial acceleration. That is the centripetal acceleration. So I can say that this is equal to b squared divided by the r. But that's not the radius of the Earth. That's all this because he's going on this orbit. So I will say for this shuttle, the value of R is 6,400 plus 700, 7,100 kilometers. Be careful with the units because they ask you meters per second. So this is equal to gravity. Then gravity is 8.14. Times the radius, which is that's 7,100 times 1,000 to convert it in meters, that's the velocity square. So you multiply, you take the square root, and you get a high velocity, which is expected to be able to orbit the planet. All right, actually, let me give you a value. So when you calculate this in the homework, then you know what to expect. With the values I have here, 7,600 meters per second. So I get a velocity, a speed of orbit, 7,000, what should I say, 600 meters per second. So 7.6 kilometers per second. Then they ask you for the period, which is the time for one orbit. For the period, okay, the period for a satellite is equal to 2 pi r divided by the orbital velocity. And r is there, so 2 pi times 7,100 times 1,000 divided by 7,600 meters per second. That would be in seconds though. They want you to find it in minutes. So once you find the answer in seconds, you want to divide by 60. So that will give you a more proper value to work with. So that's how you do it. Nothing bad so far. Revolutions per minute. You guys are gonna see a problem like that. To convert to, whenever they give you a rotational speed in revolutions per minute, remember that one revolution is equal to 2 pi radians. You always want to have this in rads per second, by the way. And you have minutes in there. So 150 revolutions per minute will be 150 times 2 pi, and per minute, in 1 minute, there are 60 seconds. This will be in rads per second. All right, so half 1, half 3, 5 pi rads per second. So in my case, I will use this number, multiply by the radius, I get the speed in meters per second. This is a good problem. So I'm gonna show you down the board. The problem they give you is a circular motion where the acceleration, the total acceleration is making an angle with the radius and the tangential speed. So that's actually an interesting problem, and actually very easy if you understand what we discussed at the end of the lecture when I talk about circular motion. So in this case, you can have a particle moving here with a tangential speed v, and we know that there is a radius, but the particle is accelerating like this and also radially. So they tell you that there is an angle between the total acceleration, which I'm going to make in this case here. I'm going to make it 30, the same as you have, but I'm going to change, and I'm going to say that the magnitude of the total acceleration is 20 meters per second squared. If that's the case, that's fine, but this is neither radial nor tangential, it's the total acceleration. The tangential is parallel to the velocity tangential, A tangential. The radial is like this. So, centripetal. So it's very easy. If I want to find that, I just do this. So I have a triangle here. Therefore, my centripetal acceleration will be, oh yes, like that. If I look at the magnitude here will be 20 times cosine 30. Cosine 30 is root 3 over 2, that's 10 root 3, which is approximately 17.3 meters per second squared. The linear or tangential acceleration, as you will think, is 20 sine 30, which give you 10 meters per second squared. That's how you do it. If they ask you for the speed, how do you find V? Well, you have the centripetal acceleration. That's equal to V squared divided by R. And they give you the radius of the circle in this problem, so that should be very easy. The last two problems, the last problem I did it in class. Let me show it to you. Remember that I also do meetings, okay? But this problem is very simple if you follow the one in the class. They give you the angle, how you are throwing this object, stone, the initial speed, so it's all following this. It's a conceptual question, sort of, okay? Just follow it. They tell you what's the final position, minus 45 or 45 meters. It's being launched from 45 meters. The idea is to find the time of flight, the initial speed. The speed in meters per second and angle in degrees per second velocity vector. The velocity vector. Okay, yeah, so here is what we did in class. When the stone reaches the ground, it doesn't reach with 0 speed. The horizontal speed is the same. And here is 21 meters per second for the initial speed. You break into components, you find the horizontal and the vertical. The horizontal is the same. The one that changes is the vertical. First it goes up and then it goes down. So don't forget that. If you look at the example from class, it should be very simple, all right? This one here is where you have to be a bit careful because it's all variables. So it's a small spring-loaded cannon launches a golf ball from the ground at initial speed VI and angle theta I. The golf ball lands at a horizontal distance of R from the launch point. The highest point is this, above the ground. In terms of R, okay, so that's not bad. And let me show you exactly, I think you will have the same problem. So they give you everything in terms of variables, and you just need to basically, if you watch the lecture, it should be very simple, but I'm just gonna go over it again here. All right, so what they give you is they give you a projectile situation, right? With initial speed. So VI theta I, and like that. And they give you this distance R. They do tell you the highest point, which is R divided by 12. Gravity in terms of gravity. So the first thing is you want to break it to components. Vi sine theta I, Vi cosine theta I. So pay attention to this. R is equal to Vi sine theta I divided by the flying time. I think that's the answer for question A, because the flying time will just be R divided by Vi sine theta I. The time takes to get to this height. Remember what we said what I said in the lecture, right? The time to go up is equal to the time to go down. So the time to go up would be this divided by 2. R over 2 Vi sine theta I. The golf speed at the peak of its path. That's easy as well. To find the speed at this point, the maximum height, there is no vertical speed. It's just the horizontal, which is Vi cosine theta I. The initial, okay, that's easy. The initial speed, just Vi. Oh, wait, you can actually calculate all this. I made a mistake. Sorry, guys. So actually, no, that's okay. Leave it like that. We haven't used this piece of information. And we can use it because we can use the vertical motion. I have the time to go up. I have the acceleration of gravity. All right. V final on Y square is equal to V initial on Y square minus 2 times gravity times the height, which is R divided by 12. The final on Y is 0. This will give me GR divided by 6 equals to the initial speed square on Y, which is Vi sine theta I square. Okay. Now, so it seems like they want values here. Wait, but it's all in terms of R, G. Suppose a golf is launched in the same speed found in D. Okay, okay. Well, no, that's fine. That's fine. We're doing everything correctly. We found this. So they want you to find the initial speed in terms of, okay, in terms of RG, you want to find everything else. So here, first, the time. So this was not the answer. That was not the complete answer. The time is R over 2 Vi sine theta I. So VI sine theta I is VI sine theta I is the square root of GR divided by 6. That's what you want. So you place this in here, so you will have R over 2 times the square root of GR divided by 6, and that will give you, well, you have to simplify. To simplify this, I will do this, R divided by 2 over root 6 over root G over root R. R over root R is root R. That's root R times 6. So because this goes up, divided by 2 root G. So this will be 1/2 square root of GR. Sorry, 6R divided by G. Don't quote me on this. You guys may have different numbers. Now that's the time to go up. So the total flying time is just that. That's the time to go up, right? So the total time will be just the square root of 6R divided by G. So that's what they were asking. So now I have here the vertical speed, right? And that's it. That's it for the problem. So it's working with variables. You find VI cosine theta I. Oh, guys, my bad. This is all wrong. All wrong. So if you guys are watching this video, guys, I'm sorry. This is a boo-boo. This is a mistake. And I hope you noticed it when I was doing this. This should be cosine. This should be all cosine. What am I thinking? Cosine theta I, cosine theta I. Then here you have the time to go up. Yeah, what was I doing in this problem? This should be double this. No, that's okay, the half, yeah. So 1/2, this is cosine theta I. Now this is correct. This is correct. So VI sine theta, that's vertical speed. Now, R divided by time is VI. So this is just R divided by time. R divided by the total time, the total flying time. But they want you to find the I have VI sine theta I, and I have VI cosine theta I. All right, guys, this is what you have to do. So if you guys are watching this video, please, I'm sorry, I made a mistake here. And this shows you how important it is to always check your answers. So I was checking my work, and I realized I made a mistake with the trigonometric values there. Here is cosine. That's the range. This is the total time. So all this is right. Now I corrected that. What you guys have to be careful now is when I find, I have an expression for VI, and the one is in terms of R and G. So the time interval. So that's not the answer. We need to find a way to put everything in terms of G and R. This gives me VI sine theta I. You could use another equation of motion, or we could no, that's fine. Final equality. We use an equation, of course. We can use the equation on the vertical. It's gonna be a messy problem, sorry. On the vertical, you wanna use the final on y equals to the initial on y minus gravity times the time to go up. I complicated myself too much in this problem. Just use that equation directly. This is 0. This will be VI sine theta I minus G, the time to go up. So the time to go up is equal to VI sine theta I divided by gravity. But finally, I do have also from here, right? So I can make these two equations equals to each other, and I can find the angle in terms of R and G, and then and I can find the time, which is they're asking you in terms of R and G, because you have this. If you combine these two with each other, this is a very, maybe I should have changed this problem from the assignment. Anyway, the time to go up is this divided by gravity. So the square root of GR divided by 6 divided by gravity. Simplify that in the assignment, okay? So that's what you want that's the first answer. Okay, I'm sorry that it was a mess at the beginning. I think I just didn't read it properly. All right. And then to find the angle, right, you can just make this equal to this. If you make that equation equals to the other equation, let's say I make R over 2 VI cosine theta I, that's the time to go up, equals to that, VI sine theta I divided by gravity. If you multiply cross, you get GR equals to VI squared times the sine of the double angle. And I found my double angle there. All right. So let's do this. Let's see what else they want you here. So we found time, we found the V, initial speed is just V sine theta I. V sine theta I is G, the time to go up. The time to go up is that, so that's that. And yeah, so once you find the expression for the time to go up, you multiply by gravity, you get initial speed. That's initial speed vertically. And you can also get it horizontally. Then you use that for the angle. The angle to get the highest height is 45 degrees. Okay, so that will give you the answer for that. All right, guys. So hopefully, I'm sorry for this last problem. I will understand if you skip it. All right. The rest of the problems are very simple. All right. I didn't notice that this problem was going to be that long, actually. So take it as an algebra exercise. More than that, if you have any questions, I will be ready for answer questions as soon as you get reach to this chapter. See you guys later.